Welcome back. I wanted to talk about one last piece of the puzzle, especially when it comes to graphs. Although we've talked about graph traversal up until now, and also tree traversal that use BFS and DFS, there's also another thing that you should consider. Now, in an interview, you're most likely not going to implement these algorithms because they're extremely complicated and they take a long time. However, an interviewer might expect you to know about them and know that you'd use Bellman-Ford or Dijkstra's algorithm to figure out a shortest path problem. But you might be asking yourself, whoa, Andre, you just told me that breadth first search is used for the shortest path problems. Why do we need these extra algorithms? I already know how to do that. And this is actually a special case. You see, breadth first search is great for the shortest path problem, but there's one thing that it can't do. It assumes that each jump to another node in a graph, if we go back here, it assumes that each path has the same weight. With a depth first search and a breadth first search, we don't really care what kind of weight an edge has. For example, in real life, such as Google Maps, some roads are faster than the others, right? We have perhaps more traffic on one road. Maybe the distance from one node to another is shorter than the other. And these weighted graphs, which we've talked about, have a number associated to their edges. Remember, a node is called a vertex in a graph, and the connection between two nodes is an edge. And depth first search doesn't really allow us to take into account these weights. We need something else. And in an interview, if somebody asks you this, your answer should either be Bellman-Ford or Dijkstra's algorithm that allow us to find the shortest path between two nodes of a weighted graph. Now, Bellman and Dijkstra are two real people that are academics, very, very smart academics that came up with their own algorithm to solve the shortest path problem of a weighted graph, such as Google Maps trying to figure out what's the closest way for you to get your burrito, for example. And just a side note, fun fact, this is Richard Bellman, and it's the same person that wrote about dynamic programming, which is an upcoming section in our course. Let's just say that both of these people are very, very smart. Now, both of these algorithms are quite complex, and it takes a lot of time to really get it and code it. So I will leave resources for you if you want to learn more about these algorithms. Because in an interview, it's very, very rare that you'd ever have to code these algorithms. Most of the time, you just have to know that they exist and when to use them. So let's go over that. Bellman-Ford algorithm is very effective at solving the shortest path over Dijkstra's algorithm because it can accommodate negative weights. So if a weighted graph has negative weights or negative number, Bellman-Ford algorithm is going to be able to solve the shortest path problem, while Dijkstra won't be able to. Now, why would you ever use Dijkstra's then if Bellman-Ford algorithm can do better? Well, we won't get into the math of it all, but Bellman-Ford algorithm can take a long time to run in terms of complexity. And it's not the most efficient algorithm. The worst case for Bellman-Ford algorithm is usually a time complexity of O of n squared. So it's not very efficient. Dijkstra's algorithm, on the other hand, is a little bit faster than that and a little bit more efficient, with the downside that it can accommodate for negative weights between nodes. If an interviewer shows you this diagram and tells you, I want to find the shortest path from 0 to 4 on this weighted graph, you now know what you should say, right? What algorithm are you going to use? Are you going to use a breadth first search, Bellman-Ford algorithm, or Dijkstra's algorithm? The answer? Well, it should be Dijkstra's algorithm. There's no negative weights on this graph. It's a weighted graph. So Dijkstra's algorithm is going to solve that problem.